All right. Hello, everyone. Welcome to today's installment of the Corundum developer meeting, live from Tokyo um, at 1 a.m. Great. Okay, so let me go ahead and get cracking. Um, there we go. All right. So today I've got some basic announcements. I'm just going to go over the sustainability stuff that I talked about, last time, just in case people have questions or comments. And then I have some status stuff to report. Next week is ISPCS, so I'm hoping to have a couple of things to show there, and then after that is the OCP summit in San Jose. So hopefully I can whatever I show at ISPCS, I'll probably also show at San Jose. Um, so we'll see. I don't have everything working yet, so hopefully I'll be able to get all the kinks worked out. So anyway, moving into the announcements here. The next developer meeting is possibly going to be on November 6th. Um, it sounds like there's a possibility that I'm going to have to attend ITSF. I'm not 100% sure about that at this point, which I think takes place, so it conflicts with November 6th, but that's in Sevilla, so maybe I can still make it work. I'm not sure. Um, I'll keep you guys informed one way or the other. The next Switch developer meeting, hopefully it will take place on November 13th, again at 9 a.m. Actually, I wasn't thinking straight when I made this slide. The Switch meeting would be next week, presumably. Well, I guess we'll see about that. We'll see about that because next week is ISPCS. Well, I'll discuss with Carlos what makes sense there, and then let you guys know.
Yeah, maybe we can keep it for next week. Yeah. So we can
Yeah,
decide it early.
yeah, a bit of a brain fart on my end in terms of making the slide. Anyway, not a big deal. Whatever works for you, Carlos. If you got stuff to present next week, great. If you don't, we can always bump that until you have enough stuff to talk about.
Okay,
Um,
sounds good.
yeah. And then I guess after the November 6th, I guess there would only be if we keep the once per month cadence, we just have one more meeting this year. Um, can't believe it's already getting to the end of the year already. That's how time flies. All right. And then there's one other important announcement that I'm going to make as well, is that as of October 1st, I am no longer a full-time postdoc at UCSD. I'm transitioning to be a half-time project scientist. And hopefully that's going to enable me to work on, more stuff independently of the university. So the Corundum rewrite, potentially consulting, things of that nature. So not being full time means that, you know, there's a better possibility of working on stuff like that without tripping over anything. So figure I would announce that to everyone just to make sure that we're all on the same page in terms of everything. And this also kind of motivates the sustainability stuff that I'm going to talk about now, right? So the research paper on the complete system that Corundum was initially developed for was presented at SIGCOM in August. So the question becomes then, well, what's next for Corundum, especially with me moving on to doing other research, right? The grant is done. Um, I'm not sure exactly what's going to become of that research going forward, but you know, question is, what does that mean for Corundum? Um, because there's potentially both good news and bad news there, right? The good news is that we're not necessarily tied to this research project and supporting what the research project is doing. But the flip side is without the support of the research project, it's a question of how do you make the project sustainable? How do we prevent Corundum from becoming yet another abandoned open source project? Now the problem is that Corundum it's a very complex project. There's lots of different pieces that all have to fit together properly, and the proper maintenance and continued development, I think realistically, is probably multiple full-time jobs. Um, and from observation, it seems like most people that are interested in Corundum, they don't really care about building it. They just care about trying to use it, trying to drop their own application logic on top of it, things of that nature. Not there's anything wrong with that. I mean, that's what it's intended for, is to run custom logic on top of it. But there has to be some people to actually maintain it and continue to develop it and build it and whatnot. Um, and it's a question of how do we make that work? And kind of dovetailing with that, Corundum has been released under permissive license, and as far as I can tell, permissive licenses on their own are not sustainable because they rely on the generosity of the community, either through some sort of donations or donated time, or as a project that's just directly managed by a company because it's useful for their own internal stuff, so they might as well release it, and then maybe other people could make use of it as well. So as a result, they're subject to the tragedy of the commons, right? People can use it without contributing anything back, and then eventually the project just kind of withers and dies. So, and the other aspect is that with the permissive license, there's no restrictions attached to it. So there's no way you can do something like charging for maintenance if there's nothing of value that can be exchanged, right? If you have a more restrictive license, then you can potentially have a commercial license that's has different restrictions that might be more amenable to incorporation into a product, and then that provides a path for making the product sustainable by bringing in funds you can use to pay developers to continue building and maintaining the project. So the potential solution, I think, is to move to a more restrictive open source license. I'd like to keep the code as much as possible open source for academic research purposes and learning and things like that. But if we use a more restrictive open source license, then that's incompatible with actually turning it into a product. Then what you can do is dual license with a paid commercial license. When I started working on all of my open source libraries, there weren't very many licenses available that actually worked properly for hardware projects. But a few years ago, CERN came out with their open hardware licenses, and they have their CERN OHL v2 strict license that basically acts like the GPL, except it actually works properly for hardware. And code licensed with that, you have to release the complete project source code for everything when distributing the hardware. So if you license with something like that, a company wouldn't take that and incorporate it into their product because of it requires them to release everything. But if you have the dual license option, then the commercial license can remove that restriction basically, such that nothing has to be released. But in order to dual license, you have to have the copyright, and that I guess you don't necessarily have to have copyright, right? I guess you could have if the code is available under a permissive license. I mean, I guess you could dual license it, but in that case, what's the point of dual licensing it? So really, the way to do it is to own the copyright and bring in contributions under a CLA. With the current code base, we would have to basically rewrite it in order to clear up any problems associated with that. But I've been considering doing a rewrite in System Verilog anyway, and doing an overhaul of some of the architectural structure of Corundum, and potentially bringing in support for some more powerful features. So if we do the rewrite and we render the code in System Verilog and we bring in some of these new features and we dual license it, that potentially opens up the door to basically turning it into a product that companies can license. And there's definitely some precedent for dual licensing stuff like this. I know the Qt windowing toolkit that works like that. They have GPL and LGPL licensed code that you can download and use in open source projects, and then they also have a commercially licensed version of basically the same thing that's a paid license that you can use for various embedded applications and desktop applications and whatnot. So be interesting to try to apply the same thing to Corundum and see how it works. But yeah, with the System Verilog rewrite, the high level idea is to basically rewrite Corundum and all the libraries that are needed into System Verilog, and we clean up, optimize, deprecate old code, and make deeper architectural changes as necessary to improve the performance, improve the flexibility, make things easier to maintain, easier to read, easier to understand, things of that nature. Potential, future features that could be incorporated as part of the rewrite is to support things like higher link rates. Higher link rates potentially means you have to use like segmented internal interfaces for streaming interfaces and whatnot. More PCI Express bandwidth potentially means that you have to run higher internal frequencies, wider internal buses. There's a bunch of stuff that I've been mulling over for improving the descriptor handling, for improving the scheduling. Um, there's also a bunch of stuff I want to do with the driver interface to further decouple the driver from the hardware, which should make it easier to support more boards and also potentially to get the driver upstreamed into Linux and or DPDK. So all of this type of stuff can potentially be, rolled into a rewrite. So that's another thing to be worried about to some extent as well. It's like if you're going to do a rewrite under a different license, then you have to be worried about competing with yourself, right? If people can just continue using the old version of the code that's available under the permissive license, then why would they use the new one? So you put all of these fancy features in the new one. Okay, well now you have a pretty significant differentiation between the two. So if you had support for SRIOV, for the improved driver, for the faster link rates, for the higher PCIe bandwidth, that could be a pretty compelling case for moving over to the new version of the code. So yeah, people have any questions or comments about that? Happy to discuss. And I think the doing a rewrite is probably going to be pretty complicated logistically. I mean, if people want to help with that there might be some options for that. At this point, it's not like I have a big pile of money or something that I'm using to fund this. So that could change in the future. I don't know. We'll see. I mean, if people start licensing it, then I, potentially would be able to hire some people on to help work on this. After all, that's kind of the whole point of licensing, is to help with the maintenance and the continued development. But I can't make any promises at this point. We'll have to cross that bridge when we get there. So that about rounds it out for the sustainability discussion. The next thing is, I guess the last thing is the status updates. I've been doing a couple of different things here. The first one is some basic measurements of the PTP time sync performance, just kind of a shakedown sort of thing. I've put some of the synchronization signals up on oscilloscopes before, and that tells you a few things. But I've recently acquired a much higher accuracy time measurement setup, which potentially can provide some more detailed insight into what's going on with the various subsystems. So I've started to take a look at that. It's very, very preliminary, but there's potentially a few things that could be learned. I've also started chipping away at White Rabbit support. There's going to be a lot of components that have to be built for that to work. So I've started working on the DDMTD. I think in a previous presentation I talked a little bit about the helper clock generation using one of the internal MMCMs. So use the internal MMCM, and then you can drive the DDMTD component. And then also, once we have DDMTD working, then you can experiment again with different techniques for generating that helper clock, and figure out which ones actually produce a better result. And then I've also done some work on the OCP White Rabbit NIC, and I have some basic results or some updates with respect to that to talk about. Not a whole lot of stuff, but a few things. All right, so for the PTP measurements, I acquired a GuideTech GT668 CTIA card. The CTIA is a continuous time interval analyzer. It's basically just a time stamper with a very, very high resolution. So these cards provide like a 1 picosecond resolution across 2 inputs. So with this, you can use it to characterize, oscillators, time to synchronization performance. They're a pretty useful tool on the timing side of things. So what I did is I took this card and I hooked it up to two different NICs that were being synchronized via PTP, and just took a very basic measurement of what the synchronization performance looked like. Right, take the PPS outputs of two different cards, And then you take the difference between the timestamps, and that gives you an idea of how well the sync works, right? If they're perfectly synchronized, then both pulses are going to occur at exactly the same time. If they aren't synchronized, then you're going to get an offset, you're going to get variance, things like that. So I did two things. I did the test with two instances of Corundum connected, and then I also did the test again with one ConnectX-7 acting as the grandmaster, and then Corundum, synchronizing to that. So the first one here is using two instances of Corundum synchronizing to each other. I used just a standard PTP4L for this, and I guess I don't have any like actual statistics from this, including variance and whatnot, but the spread is around minus 50 nanoseconds to plus 50 nanoseconds, something like that. Just difference between the min and the max. But the average is pretty close to zero. Maybe not exactly, but hunt around a little bit. If you average it, with a window or something. But there isn't some large offset really. Um, but that is quite a bit of variance here. I'm not 100% sure where this is coming from. I'm going to have to go do some digging to try to get this pinned down. There's a couple of possibilities. I think one thing that's probably going on here is the way this signal is being generated on the FPGA. I think it's being done in the PCIe core clock domain. And if that has like a spread spectrum on there, that's really going to mess things up. So I might need to rework how that's being done. It's also possible there's some other funky, control loop not being tuned quite right sort of stuff going on with the PTP time distribution subsystem. So I'm gonna have to spend some more time messing around with the hardware and see if I can figure out, where this relatively large spread is coming from and see if I can narrow that down a bit. But it's at least a starting point here. Proves that Corundum can synchronize to within 100 nanoseconds or so, although there's definitely some room for improvement. And then the next thing that I did, just to compare against a somebody else's implementation, is I used a ConnectX-7 and I performed basically the same test. And there's a couple interesting things to note. The first is that the min max range dropped a bit. It's closer to 70 nanoseconds instead of 100, which implies that probably most of that variance is on the Corundum end, right? If you have two Corundum NICs talking to each other, that's giving you about 100 nanoseconds of variance. If you have Corundum talking to something more stable, the variance is going to be reduced there. So that makes sense. But there's also a big offset of about 100, 105, 110 nanoseconds, something like that. And it's unclear where that's coming from because with the link itself, if there's any, asymmetry there, that could be an issue. The overall link length should be compensated for by PTP, and 100 nanoseconds that's a pretty large amount of time, right? We're not talking about 100 nanoseconds worth of fiber, 100 nanoseconds worth of cable is quite a coil. So the like the SMA cables that I used are exactly the same between both these tests. I don't think there's anything on either of the boards that would be introducing such a large delay like on the PPS output. So that's going to require some more investigation, right? Is the ConnectX-7 doing something funky? Possible. Not 100% sure about that. Not going to rule it out. Is Corundum doing something weird? I'm not sure. I'm gonna have to pin this down. But it is important to at least get an idea of what the current situation is, because if you can't quantify it, then you can't really improve it. And then I also just put both of those measurements up on the same screen here. So you can see over here on the left side, this was with the ConnectX-7, and then I switched to use the second instance of Corundum. So you can see, right, that offset changed, and then also the variance changed here. So It's not just some um, aspect of the graphs. There's actually a pretty significant change in the offset there. I'm suspecting that there could be something going on with the way the transceivers are set up in Corundum. So I think I might have mentioned this before. If we're going to be, say, implementing White Rabbit, we're going to have to be doing a lot of reworking in the transceivers to get the latency under control. In that case, we're more interested in the variance, but it's entirely possible there's some other stuff going on in the transceivers that are introducing some sort of asymmetry. When you have Corundum talking to itself, even though there's some asymmetry in the links, it's maybe canceling itself out. But if you're talking to somebody else's implementation, then that could be showing itself. So yeah, I'm gonna have to do some work on that and see if I can pin that down.
How,
Um
how is it sup how is it supposed to look like for a Connect X7 to Connect X7?
um
At least
I don't know if I
what
have
are
a
you
graph of
expecting?
that at the moment. Yeah. What was I expecting? Right. If we do Connect X, that's a good question. If I do Connect X7 to Connect X7, I need to dig up another Connect X7. I only have one right now set up, so it's kind of hard to do a test with only one card. Or kind of hard to do a time sync test with only one card. Um, I have done some testing with that. I think a couple of weeks ago. I can't remember exactly what the figures were, but there wasn't an offset, and I can't remember exactly what the variance was. There was more variance than I was anticipating. I thought if I was just taking the PPS output of two of these things, the variance would be relatively low, but it was still like 10 or 20 nanoseconds, I think, of variance. So definitely a lot less than we're seeing with Corundum in the loop. Um,
Okay.
but I don't think there was an offset. I think I tested with a ConnectX 7 and connected to a ConnectX 6 DX, and I did see an offset. I can't remember how big that offset was. I think I think it was less than 100 nanoseconds, but there was definitely some kind of an offset there. Versus, I guess one thing I have not done is to connect two ConnectX 6s to each other and see if I see an offset there. Right, just try all the various combinations. I'll have to do
Hmm.
that. Unfortunately, while I have two ConnectX 6s with the PPS input and output connectors, one of them was damaged on the flight over here, so I'm going to have to repair it. Some caps got knocked off of it, so I'm going to have to repair it before I can do that. Before I can do those tests. But yeah, like I said, these are very preliminary measurements. I just did this like yesterday, so um, yeah, after these conferences, I'm going to be definitely taking a much deeper dive on this to try and pin down what's going on. So the other thing too, with the way I have the PTP subsystem implemented, is that there are a couple different ways of getting like a PPS signal out of it. One of them is using the period output module, which is what I did for these tests. But the PTP hardware clock itself can also generate a PPS output. Not configurable, it's just fixed one PPS versus the period output. You can mess with it. Um, but that one is done without any clock domain crossing or anything else, so it should be a lot cleaner. I just don't have that brought out to a connector or something. So that's probably the next thing I need to do is to pull that signal out and put that on the SMA connectors and feed that into the cards, and we'll see what that looks like. That'll probably help with the variance, but I don't know if it'll do much about the offset. Um, yeah. Anyway, it's at least useful to start looking at what the performance looks like in a quantitative standpoint, because previously I've just been looking at what PTP4L reports, and PTP4L reports 10 nanoseconds or better RMS, or I guess better than 10 nanoseconds RMS, like 10 to 15 nanoseconds or something, min max. So from that standpoint, it looks like it's working quite nicely, but apparently there's some screwiness here. So yeah, need to pin that down and figure out exactly what's going on. Yeah, because if we can't make PTP work reasonably well, then yeah, there's no way we're going to be able to get White Rabbit working with high precision. All right, so I think that about rounds it out in terms of the PTP measurements that I was doing. So moving on to DDMTD. So I looked at the papers for White Rabbit that discussed the DDMTD implementation. And DDMTD, for those not aware, is what does it stand for? DMTD, I think, is dual mixer. Shoot, I can't remember what it stands for. Um, Adding the D in the extra D in front is doing it digitally. So a DMTD you use, it's basically an RF approach where you use DMTD, it's a dual mixer time difference. There we go. So with DMTD, that's done with analog mixers. It's kind of an RF technique. The DMTD version uses basically flip-flops, and it's done digitally. And the idea is that it basically performs exactly the same, except it's now something that you can implement on an FPGA, whereas you can't implement an RF mixer on an FPGA. You can do the DSP equivalent, but that's not what we're interested in here. So I went ahead and implemented the DDMPD itself, as well as they have a deglitching routine, because whenever you have whenever there's a transition coming out of the mixers, any jitter in the clocks is going to result in some schmutz basically right around that transition. So you need to use some kind of a technique to try and figure out, okay, where is the actual transition inside of that mess? And they had a couple techniques in the paper, so I implemented one of those, and seems to do what it's supposed to do in simulation. But still, even after the deglitching, there's still a fair amount of noise effectively in the output. So that has to be averaged in some way. And because this is an angle that's coming out of this thing, there's a wraparound problem involved here. So you need to make some modifications basically to the averaging, such that you get sensible results considering the wraparound. Because, for example, if you're sitting at 0 degrees, right, you might be oscillating between 0 and 359 degrees. Well, you should be producing a result around 0 or around 359. You shouldn't be producing 180. So depending on how you do the averaging, yeah, that could be a problem. So the first pass implementation I did, that wasn't working quite right, and I've been mulling over solutions to fix that. And I think I have an idea. I just need to actually implement it, test it, and make sure it does what it's supposed to do. So once I get that working, then what I'm going to do is I have a pair of U200s. I actually got nice little brackets for holding these things. But yeah, I have a pair of the U200s, the ones that I modified with the SMA connectors on there. And what I'm going to do is basically synchronize these with effectively Synchy and use the DDMTD to close the loop. So DDMTD unfortunately only works if the frequencies are already very, very close together. So what you actually need to do is use two different phase detection techniques, one of them being kind of a more coarse phase and frequency detector that you use to get the frequency right and the phase relatively stable. And then you can use the DDMTD either to measure the precise phase or to control it to a specific offset. So with that, what we can do, hopefully, is write a little bit of software to close the loop through the SI570 oscillator on the board, which drives the reference clocks for the Ethernet transceivers, and basically implement Synchy without sending a recovered clock to the PLL chip, which is, I think, kind of traditionally how that's done, and how a fair number of FPGA boards are set up. So if that works, then well, it's not everything you need for White Rabbit, but it's a number of the individual component parts implemented and integrated. And then we can also test this potentially on other boards and see if it works. The reason I picked this particular board, the U200s, as opposed to something else that might have a more usable connector on there or something, is primarily because you can actually talk directly to the SI570 part just directly over the existing I2C interface. We don't need to jump through any additional hoops to make that work. Versus some of the other boards, accessing the PLL chip is more complicated. And some of them will have to modify like the firmware on the board management chips and whatnot in order to actually do something like this. So that's a much longer term thing. I thought the hope is that if this kind of capability is interesting enough that we can get the board vendor to actually step up to the plate and add a couple lines to the firmware, but we'll see about that. So yeah, this is working in sim more or less. I need to do some more work to actually get it into a point where it'll work on the board. Hopefully, it's only take another day or two worth of work. Hopefully, fingers crossed, right? Yeah. And the other thing that I did some work on as well is the White Rabbit NIC board thing that we're working on as kind of as part of the Open Compute project. So I think I've mentioned this previously once or twice. We're using the low-cost Korea K26 system on module. We built a custom PCIe carrier board for it. Now the Korea K26 system on module, it only has one GT8 quad. So that means you only get 2 lanes of PCI Express Gen 3. Well, I mean, you could do 4 lanes, but then where you can hook up the Ethernet. So 2 lanes of PCI Express Gen 3 and then 2 10 gig SFP pluses. And then we've updated the board to have 2 more 1 gig SFPs that are connected to the LVDS/IO on the FPGA. And it's still unclear if we're going to be able to actually use those for White Rabbit because of just the way the LVDS bit slice IO works versus the actual GTHs. White Rabbit, you need the DDMTD to make the very precise time measurements. With the LVDS/IO, they don't generate a recovered clock. If you don't have a recovered clock, then you can't really use that for DDMTD. So we'll see. Maybe there's a workaround. I'm not sure at this point. But yeah, the card, it has a Renesas PLL chip, which is fractional N unit that'll give you a very, very high or very fine resolution on adjusting the frequency. And there's also a couple of SiTime DCXOs, which again give you a very fine control over the frequency. So hopefully, with all those parts, we have everything that we need to get White Rabbit working. I mean, obviously, we got work to do on the gateware side of things, but if the board has all the hooks, then we should be good to go. So the status is that we have the second revision of the board back from the fab. I got it right here, and I tested all the interfaces, and they all seem to be working. And we haven't uncovered any major design problems so far. There was an assembly problem. Not sure exactly what happened because the schematic looks correct, but an incorrect component was placed in one of the power supply feedback networks. And well, as you might imagine, that board is dead because the 3.3 volt rail was not 3.3 volts. Fortunately, we didn't plug the SOM into it. So, the PLL chip and all the oscillators are zapped, but what are you going to do? At least we found the problem and fixed it. Yeah. And I guess I have, all right, so I have a couple pictures of the board. Here's the old board, right? The Rev 1, that's the top of it, and the back of it. We had to make a number of, blue wire hack modifications to this to get it working. We had to bypass the PCI Express ref clock around the PLL chip because the PLL chip loads its config out of an EEPROM. So if the EEPROM is blank, then it doesn't load. And 2, it takes like several seconds to start up. So that means that this card would never boot in a, any reasonable computer because there's a requirement between when you apply power and when the card can successfully enumerate, and that requirement is like it's less than a second. So PLL chip would really throw a monkey wrench in that. So we had to bypass it, and then the second thing is to connect up the EEPROM to the system I2C bus or to the card I2C bus, so we can relatively easily program the EEPROM for the PLL chip. So those modifications have been incorporated into the new board design. We made a few other changes as well, and this is what the second revision looks like. Here's all the parts are, right? We've got the 4 cages over here. We got 2 10 gig cages on top, and then 2 1 gig down below. We've got a couple of SMA connectors for timing I/O. Got a USB connector here for JTAG, JTAG, and I think at least 1 serial port as well. And I think maybe it's a dual port chip, so we got JTAG and the dual port is a quad port. I can't remember off the top of my head. We got 1 JTAG and at least 1 serial port hooked up to that. And then we've got 2 lanes of PCI Express down here. The PLL chip is right over here. This is the Renesas part. And then we've got 2 SiTime DCXOs. There's one here and there's one here. And there's the M.2 GPS module. And then there's some I/O connected to the system on module. So the idea is that you can run this thing either as a PCI Express card, or you could potentially run it as a separate standalone thing. You just provide 12 volts power, and then you could talk to the SOM, plug in a keyboard, plug in a monitor, or whatever. Because this is a Zinc UltraScale device. So that's what that looks like. Like I said, I've tested all 4 of these interfaces seem to work. I did have some trouble with a couple of them. It's maybe more of a link partner problem. I think the 1 gig interfaces didn't want to link up with a Mellanox NIC. I think they should be able to do that, but for some reason it didn't work. But when I put one of the SFP to base T adapters in there, that worked. So anyway, and we got the PLL chip configured and whatnot. All the reference clocks coming out of that look correct. I think that about rounds it out for that. Yeah. That's about all I got for status updates and everything for today. If anyone has any questions or comments about any of this, go ahead and fire away. Or if anybody has anything else that they want to bring up.
So what happened to the non-PV boards?
Haven't had a chance to work on that.
So it's just that
The 3522s? Yeah,
yes,
so what was the story with those? Well, the story is that they seem to work fine, except the flash chip is locked. And
can't
I'm not sure
why
how to
can't
unlock it. What?
can't you replace it?
I mean, I guess I
Replace
could.
with okay.
I mean, they're BGA parts. I don't really feel like reworking those. And that's invasive, right? I mean, each board has 2, so you'd have to go swap all those out. It's one of these things. It's like, yeah, I could replace it, but I don't know. It's like I would rather just figure out how to unlock the darn thing, and then I don't need to replace it. Then I can just unlock any board. So I guess
Right.
I can summarize what the situation is on those things. So there's a whole bunch of moving parts on these boards, unfortunately, right? Because on the board you have a little LPC ARM microcontroller, and then you have the FPGA itself, and their default design has at least 1 soft core, which is a microblaze running on the FPGA. So there's and then there's the flash chip sitting on the board. So what I've done so far is I've put together a Corundum image that I can load onto the board via JTAG, right, using my totally hacked up little edge connector thing. And it connects to the flash, and I can read from the flash, but I can't write to the flash because it's locked, right? You got to send it the right command to, turn off the protection. Now, apparently, there is a way you can convert a PV board into a non-PV board and vice versa. And what I suspect is the technique is for that is that the flash chip is unlocked, and then the non-volatile protection bits are, programmed one way or the other, depending. Um, the the flash chips have some relatively complicated sector protection logic and things like that. I have not really delved into that. That's actually one of the reasons I haven't really worked on this, because it's like I'm going to have to read part of that data sheet forwards and backwards to figure out how in the heck this actually works. But yeah, there's a password that has to be provided. It's like a 64-bit password, something like that. So to guess it would not really be feasible. So the question is, obviously well, actually, I guess the other thing too is that I did take a look at the driver that they provide for the cards, and that registers with DevLink, and they actually have a DevLink firmware update hook. So you can take the firmware update package and use DevLink to transfer it to the card and flash it. Now, obviously, to flash the firmware update, it has to unlock the card, right? It has to somehow just temporarily turn off the protection bits. So something knows the key, but I'm not sure what. I don't know if it's the LPC microcontroller, right? And the main FPGA, sends the LPC a command to say, "Hey, unlock the flash," or is it the microblaze inside the design that knows the key? I'm not sure. So one or
The
the other,
micro
presumably. What?
the microblaze, is it the shell? Is it some kind of shell in the FPGA, or is it like
Yeah, it's in the
no?
FPGA. Yeah,
Okay,
it's in the design in the FPGA, in the whatever the default one is for the
right.
non-PV version. Yeah. So one of these components, I think, knows the key, and under the right circumstances, it will, go through the process of unlocking the flash. So it basically seems like there's a couple of different potential routes for making this work. One of them is to figure out, what the sequence is to command the card to unlock itself, basically. Because I'm assuming there's probably a couple different methods, right? It can either unlock temporarily for a flash upgrade, or you can unlock like in a non-volatile way for the converting to a PV version. So either you figure out the command, and then you just send the command to the thing, and okay, hey, now it's effectively a PV card, and you can load whatever you want on there. Or we have to figure out the key, and then we can basically do that ourselves, right? Because you can just read the manual to figure out how to flip the protection bits. It's not that hard. The thing you need is the password that gets sent to the chip. So I'm thinking, oh man, this is the only way to get this is probably to, try to disassemble some of the code here or something. And, if we have to look at a microblaze where we might not be able to access the firmware, that could be a problem. Well, it looks like the firmware actually sits in the flash separate from the actual FPGA image. Although it doesn't seem like there's very good, debug disassembly tools for microblaze right now. So, I don't think you can drop it into Ghidra and actually get a disassembly of that. So that's slightly problematic. But another option could be to try and hook up a logic analyzer and capture that way. Originally, I was like, oh man, this sucks because the FPGA is BGA and the flash is BGA. So how are you going to hook up a logic analyzer? But then I realized that they actually have two flash chips, and they have some muxes to select between the two. Well, the muxes are QFN. So potentially you can actually hook up a logic analyzer to that and probe it. And I'm actually not sure. You might only need to hook up like 3 or 4 wires for that, because a lot of the QSPI commands, they start out in SPI mode and then they switch to QSPI later. And actually haven't taken a look at the command for the password. That might be like an SPI mode command. In which case, ostensibly, if you have a logic analyzer hooked up correctly, you just start the firmware update through devlink, and bang, you have the key. Haven't tried that yet, but it seems like that might be a reasonable course of action. I mean, I could work on it, but if somebody else has one of those cards and wants to try and figure it out, great, be my guest. And then yeah, we'll have to figure out what the appropriate technique is. But do we put that in the firmware update utility, and then if it sees the thing is locked and it unlocks it, or I don't know. We'll have to figure that out. But yeah, I mean, another possibility is that if somebody has access to the proper Xilinx tool that tells the card to unlock it, well, then we can probably figure out what the command is from there, figure out what the process is, and then do the same thing basically. So not sure. There's potentially quite a few different paths there. At this point, I'm like, well, I'm going to put this on the back burner because I've got these conferences and stuff to do related to that. Once all that's clear, then maybe I can take another look at the X3522 cards. Because like I said, I purchased like 4 of them, so I would like to figure it out. Otherwise, I got 4 paperweights. So, yeah, but it just might be some time before I circle back around to that. Are you just wondering, or do you have one on your end?
No, I was just wondering because I was following
Okay,
up
okay.
your chat and I saw there was a lot of debugging. So I was kind of interested, like, okay, there were, yeah. So I was thinking how these things interact with each other because it seems like there are a lot of startup codes uh,
Yeah,
in
yeah,
the
yeah.
FPGA.
It sounds like the coding style of a couple of the components are kind of weird, and a lot of things get like copied around, which I guess in some sense makes sense because, um, yeah, I actually don't know exactly how their microblaze is set up. There's multiple ways you can have a core interface with flash memory. So one option is to do what's called execute in place, where the core can basically request instructions on the fly and run directly out of an external memory. It's going to be slow, but you can do it. That's one option. Another option is you basically have a little bootloader, which is smart enough to talk to the flash and read the contents and write them into an internal RAM somewhere and then run that. And then there's probably some various intermediate solutions, like you can start XIP and then copy that way as well, several different options. So I don't know what they're doing, but it sounds like whatever they're doing is a little bit funky that results in things being copied into weird locations, and it's a little bit hard to keep track of what's going where, if you're putting that in a disassembler to try and figure out what the code is actually doing. But yeah, I've not been the one working on that. That's who was looking at that? It was in the boards panel if you wanted to. I think it was the boards panel anyway. Yeah, I guess that was Yaka. Not sure the correct pronunciation of that. But yeah, the boards panel if you want to follow along. I don't have anything to add at this point, but yeah, maybe when I get back, we'll take another crack at that.
Mhm.
Somebody else have something they wanted to say?
Hi, Alex, it's me. Uh,
Hey,
so I just have comments regarding the non-zero offset of PTP
yeah.
accuracy. We find similar things between port interface switches.
Oh, interesting.
The offset could be around tenths of nanosecond. I don't remember the exact number, but the range is at tenths of microsecond, tenths of nanoseconds offset. and this offset is different between different pairs of ports, even. So
Different pairs of ports, different
ports,
pairs of
yeah,
ports. Okay, so if you
ports.
take like port 0 and port 1, well, okay, so how are you doing this measurement? Like you take two
ports
PTP
in
leaf
the
clocks
same
and then
switch.
you what?
Uh, yeah, so we just pick two ports in a single switch.
Mhm.
So we can share the clock. We know the ground truth clock offset is 0. And after it runs PTP 3 messages and we get a calculated offset, and we know that, yeah, we know the sync error.
So you're getting the offset from PTP itself, or
Yes. So we have so we just run a simple 3 message exchange and we calculate the offset. It's not the standard PTP protocol. We just implement a simplified version in the Tofino.
Okay.
And we
I guess
pick.
maybe yeah. I guess I might not be following completely because in my case, if I run PTP4L, it doesn't show an offset. PTP4L does not report a large offset or
I
a
see.
large delay.
Uh, yeah, so we run it in the Tofino switch and we implement the message exchange and offset calculation in P4. So we get offset at the data plan. We didn't call the kernel version of PTP.
Right. But my point is that if you're running just the PTP protocol, then you might not see the offset. The only reason I'm seeing the offset is because I'm measuring what the clocks are doing externally to what PTP4L is doing. So that implies that there's something like at the physical layer probably that's introducing that offset.
Yes. Yeah, that also was my thought too. So what we did is just actually we picked two ports and let them send data timestamps and calculate offset based on that. And we can get a calculated offset. And if the synchronization works perfectly, this calculated offset should be 0. And after thousands of synchronization, we get a distribution just like what you got. And this this mean average of this distribution is not 0. It's always like tens of nanoseconds off compared to 0. Yeah, and this offset is even different in different port pairs, and that's that's what we found. And right, my
Seems
guess
like
is
it
also
might make sense to kind of map out the switch and see, are there particular ports that are better than others or something, or is there just kind of a
right.
slope across all the ports or something? Yeah.
That so our guess is just the timestamping is not accurate or as accurate as other ports in the Tofino switch. And it's quite interesting to hear that this phenomenon also happens in Corundum and CX7. So one of my guess is that timestamping error, this constant error could be different in different platforms. Maybe that's why you see offsets between different devices.
Well, right. I mean, when I did the testing between the CX7 and the CX6, there was an offset. So it seems like unless you're being very, very careful with the design of all the physical layer components, it's probably relatively easy to get an offset in there.
Sure.
When PTP synchronizes. And if you really want to be accurate, well, you have to figure out how to remove that offset. I guess there's two approaches to that, right? One of them is that you can adjust the design such that there isn't an offset. And then the second one is that, well, if you know what the offset is, you can just subtract it off. So, but yeah, you actually have to know what the offset is to subtract it off. So I don't know which one is a more sensible approach, right? It's like,
to know the offset, you need to know the
probably if you want to subtract it off, what you'd have to do is calibrate it. And to calibrate it, you got to have ground truth. So
Yeah.
it's like, okay, if you have two devices that are, behaving differently, how do you know which one is actually, correct?
Yeah.
If you want to do some sort of a calibration or something. So, um, yeah, it's the kind of thing where am I going to fix it in Corundum like in the short term? Probably not, right? It makes sense to try to figure out on some level what's going on. Like, is there like a really obvious thing that we're doing incorrectly? Or is it something where I just need to go through and take a very, measured, deliberate approach? And when we rebuild the PCS logic, to make White Rabbit work, okay, well, now we can go in and figure out exactly what the delays are, the various components, and how to get everything into exactly the correct mode for the not necessarily the lowest delay, but the most consistent, well-known, well-understood, well-behaved delay. So I know there are other applications where you want the lowest possible delay you can get. In our case, it's not so much that we want the lowest possible delay; we want the most consistent delay. And I seem to remember the White Rabbit guys had to play some dirty tricks to make it work. So we'll probably have to do some similar stuff, but we'll see. But yeah, no, this is the kind of interesting stuff when you start really digging into things at a low level, you can discover some interesting stuff. It would be interesting. So it sounds like you guys are doing protocol level measurements. It would be interesting to try to do something more physical layer and see if you're seeing similar results as well.
Yeah, probably we should buy a same or same accurate time card as you did.
Right. I mean, from what I can see, there's a couple of pieces that are needed for this to work. I mean, obviously having the time measurement card is important, but you also have to have something that can synchronize via PTP and then generate the pulse per second signal and do that accurately. And Corundum apparently can't do that right now. I don't know. I don't know if we use ConnectX-7s or something instead of Corundum, if that would be a lot better. That could potentially be an option.
Sorry, I didn't follow. So the first part is get the ground truth, and second part is generate
Well,
signal.
okay, so what you're interested in doing is not measuring one pulse per second signals, it's measuring the sync accuracy, right? So you want to time sync a couple of devices and then,
Yeah,
independently measure what you actually got. For that to work, you actually have to be able to produce very clean, precise one pulse per second outputs, right? Because if you can't do that, then you can't measure it accurately, right? So Corundum obviously right now has some issues with generating the one pulse per second outputs in a clean way. At least I
I see.
think there's some problems there. So I'm just make me wonder, what other component could you use, right? Would a ConnectX-7 work? Well, I mean, we've I've tested ConnectX-7 versus ConnectX-7 and ConnectX-7 versus ConnectX-6, and in various combinations you can get offsets. So, if you want to do this accurately, how are you gonna do the ground truth, right? You don't you want to be measuring basically you want to be measuring your switch. You don't want to be measuring your the PTP slave components, but you know they are part of the measurement, so you're going to be
Right.
measuring them one way or another. You got to make sure that they're well behaved. And the question is, okay, well, how do you determine that?
Yeah.
That's tricky apparently. So,
Yeah, its
well,
methodology
we'll
and
see.
synchronization is kind of complex.
Yeah, if you're interested in this card that I have here, let me show you what this thing looks like. Where did I put my screwdriver? No. Way too much equipment in this very small room here.
Did you bring mini ITX with you?
Mini ITX?
Yeah, the the mini ITX motherboard and the CPU. I'm not sure which one was that.
Do they make a mini ITX motherboard that'll take a Xeon scalable CPU?
They do, but it's a single socket with SODIMMs.
Oh, okay. Yeah, the one that I have right now, It's not a full ATX. It's not a mini ITX. It's somewhere in the middle. Anyway, this is what the
Micro
card looks
ATX,
like.
micro ATX.
Maybe I can't remember what all these freaking form factors are. Yeah, this is what the card looks like. So it's got a whole bunch of SMA connectors here. That it's really only the first two that you use for these are the two timing measurement channels, and there's like reference clock input. There's like an arming input, and then a couple of sort of general purpose outputs. But yeah, it doesn't need a lot of PCI Express bandwidth. Um, but you know, this is the one from Guide Tech. Should say, yeah. And I think they make these with a half picosecond resolution now. So they're not cheap though. That's the I mean I'm doing some collaborating with those guys since I have a couple of their cards, but yeah, potentially with the when I get the little test bed set up in my garage operational again, might be able to provide access to some of this hardware remotely. So we'll see. Somebody wants to do something with these cards, let me know. We'll see about setting up something. Anyone else have any questions or comments?
I just wanted to ask you if maybe you can share with us what you're going to present at the Plugfest part of the ISPACS conference.
Still trying to make it work. I mean, hopefully, let's see. You know, worst comes to worst. I mean, I have a, I mean, I have. Let's see. What I've read so much. I've read so much hardware here. I mean, one thing that I'm hoping to get working is the basically Synchy demo between a couple of the U200s. So you know, I have two of those. I picked up these stands here in the Akihabara like a couple days ago for these guys, so they can be, you know, set up nicely instead of just laying them down on the back. You know, they can stand up nicely. So I have these all set up.
Cool.
And then those, you're wondering how I connect them to the computer. The motherboard that I have has MCIO connectors on the motherboard, so I actually managed to find some PCIe MCIO breakout cards. You can see that there. So there's two MCIO cables going into it, and then there's a by 16 slot. So I have two of those, so I can just have those on the desk next to the computer. So that's actually kind of a slick setup. Otherwise, these cards are actually too long to go in the case that I have. So, and the other thing that I have is I got one of the Thunderbolt external enclosures. I guess this is from a company called Sonnet. I had to make a few modifications to it just to get stuff to physically fit. Yeah, so this one has the cover off right now, but I have a couple of these silicon FPGA boards in here. I had to notch out the end here so the cards would fit. I think I had to cut the back off one of the slots too. But yeah, this is the one I was using for those measurements that I showed earlier. So this, I was just using these two cards synchronized between the two, and then these have the SMA outputs that I can loop over to the time measurement cards. So, you know, I can use just PTP to sync these. If I can get a traffic generator working, I can use these to generate traffic for the switch possibly. We'll see about that. Maybe that might be more interesting for OCP Summit than for ISPCS, maybe. And then the other thing that I was trying to get working is the PTM with the Agilex I series board. So that's one thing that I have in this little computer over here. Yeah,
That sounds like a lot of things.
Look up what. Yeah, a lot of things, and none of them are 100% complete yet. So that's slightly problematic. What's another book that I had in there? It's a Super Micro. Microwave like a million different boards still. Let's see, I have the manual for it. X13 SEM. I'll pop that in the chat in case people are interested. Was courtesy of Ahmad at Meta gave me that board and also a CPU for it. So I've got that with a 6430. What does it say what the yeah, okay, it's a micro ATX.
I see.
So yeah, the board itself has two Gen 5x16 slots, and then it's got effectively two more slots via the MCIO connectors. So you can hook up four Gen 5x16 cards to it, ostensibly. Assuming the signal integrity through the MCIO stuff is good enough to actually hit that speed, which I don't know. I need to get a Gen 5 card and see if it'll go that fast. That's
Really
on
cool
my
board.
to-do list. Try to get a couple of I get a couple of the 400G NICs, the ConnectX 7s. Yeah. Actually, the ConnectX 7 that I was testing with here is I guess it's also an engineering sample board that it's their PTP Grandmaster timing board thing. It's not it has four, I guess 50 gig SFP56 ports on it, and then it has PPS in and PPS out and some kind of high stability oscillator on the board. Seems like a pretty nice board.
Yep.
Yeah, the ConnectX 6s, they have the PPS in and out, but they don't have a high stability oscillator on there. They're, I think, just a normal ConnectX 6DX with a couple extra connectors on there.
Yeah, I guess maybe that makes the Connect 7 more expensive because of just oscillator.
I mean, yeah, I don't know what the story is with these particular boards because I don't know if they've actually like officially released it as a product. I mean, it's in some of their documentation, but I don't know if it's like an orderable thing or
Okay.
not at the moment. It's not the normal connect. It's a just special version of it.
Yeah,
I
yeah.
don't know what the actual part number is, but see if I can look it up really quick. I hate these useless data sheets. It's one page. All right, it's 2 pages, but it doesn't really provide any useful information. This one, pick 7 adapter cards. Port SFP56. I think that's what we want. But I think they have two versions of that card. I guess that's also not the right manual.
Well, don't worry, Alex.
Yeah, I can't remember what the exact part
Sorry.
number is, but it's a relatively specialized timing specific thing. Also, courtesy of a mod. They have a lot of oddball stuff over there.
So this week I fixed an issue because of BIOS, and that was a crazy,
Oh.
crazy thing. It was very crazy because looking at a CPU going to 400 megahertz is not a nice feeling. You have to rub your eyes too much to see, okay, maybe you are seeing something wrong.
400 megahertz?
Yes, 400 megahertz. It was dropping to 400 megahertz and not on CPU, well, not on any time. And I set the governor and I set the clock frequency to 2.45 gigahertz. And I asked CPU not to go any below that. And only when I do IPOP test, it used to go 400.
Hmm.
Yeah. So that was
Interesting.
rough.
So that was a BIOS issue or what?
Yep. So then I searched and in some remote forum somewhere I found some people discussing about this Supermicro motherboard which has the same issue
Oh boy.
and uh, and then I had to update the BIOS. It fixed the issue.
Well, it's always nice when updating solves problems. It doesn't introduce new ones.
Yeah.
Because that happens sometimes, right? You update, and it's like, okay, well, it fixed problem X, but then it caused a different problem.
Well, my favorite's whenever they change the root hub layout on the PCI Express devices. So all of your NICs get
Ah,
renamed. And now all your
yeah,
static assignments are broken, so you can't reach the machine that you just updated.
yeah.
Very
And the crazy part is, let's say you are having a LDAP server or something, right? And you have somehow a static design, and this PC has to authenticate through that NIC. And now static IP is not there. It cannot reach the LDAP server. It can't authenticate you.
Yeah, that's a
Yep.
problem. Yeah, something
Yeah.
like that happened recently with the little cluster that we have set up at UCSD. I don't know what the heck got changed, if it was a kernel update. So I don't think I updated the BIOS on that. But yeah, since the network device names changed. It wasn't the numbering. There was like some suffix or something got added or removed or something. Can't remember exactly what happened.
I think it was
I'll
like
take a look at the
6.8. They changed the device renaming so that they made it more uniform across different device trees or something. There was
that's
some.
possible, yeah. Yeah, I can't remember exactly what happened, but I seem to remember we I rebooted the thing after shuffling some stuff around and everything looked fine because I was, in the machine room. So it's like, oh, boot it up. Okay, we're good. I go home and I can't log in. Like, ah, crap. Ah. And then I hadn't set the IPMI password on that one, so I couldn't log into that either. So, what are you going to do? Yeah. Oh, the other one that I've noticed a couple of times is it seems like there's a couple of different ways the PCI Express devices can be numbered. One of them is that they can be numbered based on the bus numbers, and the other one is that they could be numbered based on the slot numbers. Um, and I've had computers switch between the two for no apparent reason. Like sometimes it's numbered with the slot numbers after you run an update or something. Now suddenly it's numbered with with the the PCI Express device numbers. So or the bus numbers. So there's
I could
some
imagine
funky
that's
stuff going
something to
on.
do with like CSM or something like that on the UFI side, where it's
I
trying to
don't
get some
know.
compatibility.
Possible. I think I noticed I think I noticed a BIOS setting at one point about slot numbers and being able to turn
Hmm.
that on and off. But I don't think I've touched that setting, so
Yeah, that's
I
true.
don't know. Some weird stuff, some gremlins causing trouble.
Always the firmware.
Also, I in the data center room, I found a cable, a DAC cable. And I thought, okay, let me not go back to the lab and get a cable. Let me use this. And I was actually thinking before using it that I should not use a lying around cable. But I used it anyways. And the moment I used it, the interface showed up, and then I set some IPs, and then I start some pinging or something. And after like second or two, the interfaces disappear. Like not the interface, but the IPs disappear.
The
And
IPs disappeared.
yes,
That sounds
I
like
don't know.
network manager causing trouble.
And yeah, then I changed the cable and then it was fine. Too many
Yeah.
debug things.
I had a similar problem with that with one of those QSFP 28 breakouts. It was just like a bad quality cable, and the links would say the fine, that would say the IP is up. It would try to pass traffic and then just fall over on its face.
Oh
And I
man.
replaced the cable, and that was the problem.
Yeah, well, so one thing about the QSFPs is that if you're not super familiar with them, it's possible to plug them in upside down. and then it's not obvious what the problem is. So, yeah, I think I've helped at least one person. They're like, oh, I plugged everything in, but it doesn't work. I'm like, well, it sounds like it's not plugged in all the way. Can you check it? And
It
after a
doesn't
few
click.
iterations, it's like, oh, the connectors are upside down.
No, but the moment is like, then you wonder, did you break something on the process of doing that? Is something is broken in the connector? But apparently not. I think they made connector
Well,
also, but
yeah. My understanding is the way those things are designed, there's a little metal tab on the top that prevents you
yeah,
from inserting it all the way if it's
yeah,
upside down. So, um, yeah, like you can't put it in all the way. But
yeah.
if you're not familiar with it, hey, it fits. It goes in until it stops. Should be good, right? Yeah.
I have found some like Intel cables for SFP pluses where if they aren't pushed, like if you don't push the cable in while you're pulling the retract latch, the housing will just get stuck on the card. And so you can't actually get the cable out. So you have to
When you
like
try to remove it, oh
it,
yeah,
yeah, when you try to
SFPs
pull the cable out.
suck.
So bad.
Yeah, no. So we've had similar problems um with some optical modules, same kind of thing, to the point where we've had to disassemble the Frappin server and take the NIC out to
Yeah,
get the
those easy
frickin' module out.
Yeah.
Just because of the terrible design. So like I think with the modules that we had, they to release it, they pushed a little thing out the back of the module. And if it works properly, it goes under the tab, and it
Oh,
lifts the tab up. But if it doesn't work, then it goes over the tab, and now you're hosed.
And now it's a jam.
Yeah, because now the tab is stuck, and you can't. And
yeah.
then due to the way things are configured in the back of the server, the module is recessed. So there's no way you can get at it without pulling the server out, taking the whole NIC out and everything. And it's like, oh, yeah.
That's
As
sad.
much as yeah, there's definitely the right way and the wrong way, and lots of wrong ways, I think, for how to make SFP modules, how to do the retention on those things. I think the only ones that actually work properly are the ones where it lifts a pin up, because that one's guaranteed to work, right? You leave the little tab alone, you lift the pin up.
Right.
Actually, I almost think the way they should have done that is just had a hole. Instead of having a little spring-loaded tab, you just have a hole. And then that forces the module to actually latch into the hole properly. Um, yeah. I guess with the QSFPs, they use a totally different retention mechanism. They have the two little metal tabs on the sides that snap in, and then when you pull on the tab, it pushes those out. I mean, those I guess can still potentially fail, and that's going to be harder to deal with because those little tabs. I mean, how do you get access to those tabs? I don't know.
You have
I
to call a
wonder if
lock.
somebody has a what?
You have to call a lockpick guy with all the shims to get the
Yeah,
shim.
yeah,
Yeah, I was going to say, I wonder
yeah.
if somebody makes little shims that you can slide down there and release the module that way. Because that seems like it should actually work. Yeah. So that when I got this Viavi network tester, I got some. It has a CFP2 slots in it, and the first module that uh, in trying to figure out how to connect that tester up to anything useful, I ended up picking up some CFP2 modules, and when they came in, I got one. I stuck it in the slot. I'm like, okay, that looks good. I go lift the tab. It doesn't come out.
Oh no.
Yeah, it turns out that just the way the the pieces of the CFP2 fit together, there was a notch at just the wrong spot to hook onto the little tab in a way that the release mechanism wouldn't work. Well, I guess it came out a little bit. Like the release mechanism released it off of the first part of the notch, and then it got stuck on a little groove slightly further down. So yeah, I can't remember how I got it out. I think I was able to pull the test card out of the unit and pry the tabs up, which was a pain. And then yeah, I took the Dremel to the modules to fix that problem. Yeah. Anyway, definitely learn how not to make some of these things after messing around with them for a while. It's like, yeah, okay, if you do that, it's gonna get stuck. Anyway, does anyone else have any questions or comments about anything? Other stories about weird optical modules getting stuck? I don't think there's anything else I have interesting here to show off. Yeah, I'm not really, I guess, at the moment. Yeah, I'll definitely take some pictures of whatever setup I have at ISPCS and or OCP Summit. Put those in the next presentation, and details of whatever the demos end up being. So, should be interesting. Yeah, I don't know if anybody else is going to be in Tokyo aside from, from Joe, and I don't know if anybody else is going to be in the Bay Area for the OCP Summit. So, certainly happy to, try to cross paths with anybody, meet up for, a meal or whatever. Just let me know.
I will be in the OCB Global Summit in San Jose.
Right.
So,
Yeah. We've been communicating over that a little bit, right? And
exactly. Yeah.
demos and
But
such. So
yeah, do you have a paper in the Japan conference, the Tokyo conference, the ISCBCS?
not a paper, but short talk.
Okay,
So
good.
yeah.
Maybe you can send us the presentation or slides later.
Yeah, I'll send them to you when they're done. Another thing for the to-do list. Gotta finish those off. Yeah.
Anyway, good meeting. Thank you very much. I have to leave now.
All right. Sounds good. Take care.
Have a nice trip in Tokyo.
Yeah, we'll do.
Sure. Bye.
All right. So does anyone else have any questions or comments, or should we adjourn until next month? Julian is clearing out of here. All right. See you later, Julian.
Yep, I think we should let you sleep. It's
Get some
already, I
sleep.
think,
Yeah.
midnight.
All right. Sounds good. We'll talk to you guys later.
It was good seeing
Very
you.
Thanks for
nice.
tuning in.
Thank you very much.